Sequential control, conveyor systems. In this presentation, we're going to be looking at the specifics behind how a conveyor system is typically operated. Sequential, as we know, has to do with the forming or following of a logical order of sequence. And so we're going to be following through the relay logic required in order to get a typical conveyor system to function as would be expected in the electrical industry. To follow the sequential order in a schematic, an electrician must work slowly and methodically to identify the present state of all the pilot devices in the system, identify which loads are then energized by the pilot device states, identify if energized loads, such as relay coils, will cause a change in state of further contacts, and identify which loads are energized then by those relay contacts. Once we finish that, we must return to step one because as the system operates, pilot devices will change state. Conveyor belt systems often are used in multiple ways to either elevate or to bring material to a different location. They often utilize more than one motor, and that's because of the way in which the conveyor belt system has to be designed for multiple direction changes. Especially when we are going up or down, there needs to be ways to have independent control of each conveyor section. And when we have equipment or materials on a conveyor system, the order of which each one of these sections is started will become very important. Large conveyor systems are started and stopped in stages, not simultaneously. This helps to reduce the total inrush current on the system when starting the system, and it also reduces total supporting infrastructure shock when stopping the system. The order that we need to start and stop then becomes fairly important. We're always attempting to ensure that any leftover materials on a conveyor system will not back up and become obstructing any pathway along the conveyor if it had been left on there when the system had stopped. And to get to this end result when starting the system, the last conveyor is started first. The next conveyor is then started upstream and the next conveyor upstream. And this ensures that if anything is on the conveyor system overnight or something like that, the material will not be deposited onto a stationary belt. So in this example above, conveyor belt number 3 would be started first in the morning, then 2, then 1. When we stop the system, the first conveyor is stopped first. The next conveyor is then stopped downstream and the next conveyor downstream from that. And this ensures that if anything is still on the conveyor system when the stop is pressed, it will be fully transported off the belt system entirely prior to being shut down. Here's a typical relay logic system for a 3 conveyor belt system. We have 2 time delay on energization relays and 3 time delay on de-energization relays, which then control the starting, stopping, and holding of each of the conveyor's motor starters. So we have 3 motor starters, and as you can see, it looks like a low voltage protection circuit where we have a starting contact, a stopping contact, and a holding contact. Let's see how the system operates. We first start with the system energized, and we're going to press the start push button down. In doing this, we energize the C coil. Now remember, the contacts for C coil will now change state, and there are 3 of them in this particular circuit. They're all normally open, so they will now close. In closing, what will happen is we establish a holding path underneath the start push button, but we also energize all of our time delay relays. We can then release the start push button, and because TR1 and 2 are both time delay on energization relays, they will start their timing sequence now. Now, the TDOD relays, TR3, TR4, and TR5, those will not change state. uh, Like they won't have a delay in change of state because they're time delay on de-energization. That means they'll change state immediately. And so those three contacts are identified below. They change state, and now we have a full path for the M3 contactor. And what this means is that M3 starter is now the coil has been energized. All of the contacts will now change state for the M3 coil, including the power contacts, which are not shown in this particular diagram. Now conveyor belt number 3 is started, and the holding path has been established. Eventually, TR1 will time out. Let's say 15 seconds has elapsed. TR1 is controlling the TR1 normally open contact for motor 2. It will now close, energizing the M2 coil, which will then cause the M2 contacts, including the power contacts for the motor 2 conveyor, to then close, and that will cause the motor to start up and the second conveyor to start turning. We now have a holding path in place for the second motor. Finally, my TDOE 30-second relay will finish timing, and once it finishes timing, it's going to change state for the TR2 normally open contact. It will then close, energizing the M1 coil, which will then result in the M1 contacts, including the power contacts for the motor 1 to go closed and for the motor to start. We now have a holding path in place for motor 1. At this time, the system's just going to simply run. There's going to be nothing that is going to further time until we press the stop push button. So when we started the third conveyor first, then conveyor 2, then conveyor 1. Let's now press the stop push button. When the stop push button is pressed, it de-energizes the C1 coil, which causes all of the C1 contacts to return to their original state. These are the three locations. This will cause a de-energization of all of our time delay relays. And since we have 3 time delay on de-energization relays, there will be a significant time gap for those 3 contacts. So let's see what happens. It opens all the contacts. My timer relays all de-energize, and notice that M3 still running. However, now there's only TR5, which is ensuring that it stays energized. TR1 and TR2 are also going to de-energize, and that's because they're the time delay on energization relays, TDOE, and we know that there's only a time delay when they are energized, no time delay when they are de-energized. So those will change state as well, and this is what we're left with. So now the timing sequence starts. When we press the stop button, we're not intending that the whole thing should shut down immediately. Instead, we see that there would be a minimum 15-second wait time. So the 15-second wait time, finish timing TR3 is the first one that's going to be opened. And when it opens, it is going to de-energize M1, which should then cause all of the M1 contacts, including the power contacts, to go back to their original state. Motor 1 or conveyor 1 is now stopped. Further timing continues, another 15 seconds elapses, and we have the second, or TR4, second time delay on de-energization relay de-energize. TR4 is now going to go back to its original normal state, open, de-energizing M2 coil, which will cause the M2 contacts, including the power contacts, to open, de-energizing the second conveyor. And finally, my last TDOD relay, the 45-second one, TR5, is going to finish its timing, open its contact, de-energizing M3 coil, and causing the M3 contacts to return to their normal state, de-energizing motor 3. By using 5 time delay relays, we can orientate the sequence of operation for a 3-motor conveyor belt system so that the order of start is opposite from the order of stop.